Ho ho ho! Welcome back. In the last episode, we saved Christmas from memory leaks by implementing the rule of three. We learned that if our nice list manages a raw pointer, we need a destructor, a copy constructor, and a copy assignment operator. But Christmas comes but once a year, and Santa has a need for speed. And allocating new space for copy operations? Boy, that's slow. Today, we look at two more rules: move constructor and move assignment. But before we do that, we need to decode some C++ terminology, L values and R values. Very briefly, think of L values or locator values as objects that have a permanent address, like a house. They appear on the left side of an assignment. Examples include variables like A, P, reference of P, or C. They have a name and they sit in the memory waiting to be used. R values, on the other hand, are temporary. They usually appear on the right side of an assignment. Examples are number like 6, 7, or temporary results like x plus y. What's special about our values is that they don't really have a name. They are fleeting values about to be destroyed. In our code so far, we've used a single ampersand to pass L values, like so. But to catch these fleeting R values, C++ uses the double ampersand. As you can see in this example, the function L takes a single reference and works with variables like A, reference of P, plus plus C, but errors out when we try to pass a fleeting value like 13. Meanwhile, the function R, which takes a double ref, does not work with the L values and only works when we give it a temporary value like 17. So, why do we care? Because of std move, like so. Since we can't refer to our values again, for efficiency, we can skip the deep copying operation that are usually the most expensive part of the whole process. Std_move is not a copy, it's a transfer of ownership. That's why C++ provides for a move operator for efficiency. We use std_move operator to typecast a value to its R value. The idea behind move is that the object has become a R value and it won't be referred to again. Just like a temporary value, 13. We can't refer to 13 again, can we? We use std_move to steal the reference from a variable and we nullify anything that's in the object. Let's look at a code example to understand this. We start with the nice list code where we left it last. We've modified the print function to print the address of the raw pointer so we can track what's happening. Here, Santa creates a list V, an elf copies it into W, and another elf copy assigns it to U. We run this code and we see what happens. As we expected, three different allocations: slow and expensive. Now let's implement the move constructor. Remember, double ampersand means move. Move constructor is actually simpler than the copy constructor. So what we do is we just steal the resource and steal the size, and crucially we set the source pointer to null pointer. Right? And we do the exact same logic for move assignment. The guards for chained and self assignment remain in place. And again, we steal the pointer from the source, steal the size, and again nullify the source object. Now let's compile and run. This can't be const. Perfect. We see that the addresses of the raw memory remain exactly the same. No new allocation took place, just the ownership of the list pointer was moved first from the Santa to the elf, and then from the elf W to the elf U. And just like that, we have converged on the rule of 5. These are the 5 key operations that any robust C++ class managing raw memory should handle. Destructors, copy constructors, move constructor, move assignment, and move constructor. If you can write this, if you have followed and understood this, you are already writing standard library level code. Give yourself a pat on the back. Speaking of standard library, let's talk about unique pointer. Our, now, our nice list now has good move semantics, but it can still be copied and we can work on multiple independent copies. Very confusing if you have just one nice list. Now, imagine Santa wants to be strict. He wants to ensure that there is only one master list in existence. Yes, it can be passed around between the elves, but there are no independent copies of that list. That is exactly what std unique pointer does. To turn our nice list into a unique pointer, we simply need to delete the copy operations. We can use the delete keyword in the class definition. Simply like this. Now, if an elf tries to make a copy, the compiler throws an error. The list can only be moved, never duplicated. See, it throws an error because we have deleted the copy operators. But we can still use std_move to move the list around. Like so. Wow! And just like that, you have created a fully functional, robust, unique pointer. By correctly handling the move semantics and deleting the copy operations, we have built the exact logic that powers the standard unique pointer, minus the templates, of course. Santa's list is now safe. It can't accidentally be copied, double freed, or leaked. But there's a catch. Right now, Santa is a bit lonely. He can hold the list or he can move it to an elf, but they can't both look at it at the same time. What if Santa needs to share? In the next episode, we're going to implement reference counting from scratch to build a shared pointer. If you learned something new today, hit that like button. Please share, don't gatekeep, and Merry Christmas. I'll see you in the next one.